Okay, so for question 22.6, it just asks us, we're given pairs of compounds, which one is the stronger base? So when we're talking about a stronger base, it means that our lone pair is going to be localized. So localized lone pair, okay? Whereas the weaker base is going to have a delocalized lone pair. So if I color code these, I'll leave the first one in black and I'll put this one in blue, okay? Which one is going to be delocalized? The lone pair in black or the lone pair in blue? Which one is going to be delocalized? Could anybody answer that? Which one would be a delocalized pair of electrons? So I'll put these ones in black, or sorry, those ones in blue, and these ones in black. Yeah, exactly. It's the one on the right, isn't it, Mustafa, right? Because this pair, you could draw a resonance form like this. So those ones are delocalized. The ones on the left one are localized. So this is going to be the stronger base. So we'll put a circle around this one, stronger base. Okay, now in the next one, it's a little bit different. We know that the lone pair on pyrrole, so if I highlight this lone pair in black, we know that that lone pair is required for aromaticity, okay? So that lone pair is delocalized, right? We say that it could be delocalized like this, whereas this lone pair, I'll highlight it in red. If that lone pair was able to be delocalized, that would mean that this compound would be anti-aromatic, because then you'd have a 4n number of electrons in a continuously overlapping system of p orbitals, and so therefore we don't want that to happen. And so this lone pair is going to be in an sp3 hybrid orbital, because that way they're not delocalized, and so they are localized. And so that means that this compound is going to be the stronger base. Now, if I look at the next two, so if I highlight this one in blue, and if I put this lone pair in red, which one of those lone pairs is going to be delocalized? The blue one or the red one? Delocalized. It's going to be the red one that's delocalized. Why? Because you could draw a resonance form like this. So you'd say this pair is delocalized. This pair here, there's no resonance form. This pair is localized. And so the localized is going to be the stronger base. And then for the last one, it's kind of the same thing. This lone pair here, this is required for aromaticity. So this pair is delocalized, right? We could draw a resonance form like this, but on this ring, right, the lone pair, both the lone pair and the pi bond can't be involved in resonance. It's only the pi bond. So therefore, this lone pair is localized. Come on, localized, and therefore this one is going to be the stronger base. There we have it. All right, so if we're thinking about ranking these in terms of increasing basicity, if I put a lone pair here, a lone pair here, and a lone pair here, we can see they all have one methyl and two aromatic rings. But on this one here, we have an electron withdrawing group, and we have an electron withdrawing group here. On this one, we have no substituents, but methyl groups are electron donating groups, So if we have electron donating groups, those are going to donate electron density, right? They're going to be donating electron density this way. So that's going to mean that the one with the methyl groups is going to be the most basic. So most basic, because you have electron density being donated towards the nitrogen, and the one with the electron withdrawing groups is going to be the least basic, because they're going to be pulling the electrons away from the nitrogen based off of their electron withdrawing effects. Okay, so that brings us to section 22.4. This is the last section that we'll cover today, and this is just review. These are all concepts that we would have seen, but they might not be in your mind right this second. So let's take a look. The first one is, excuse me, making a primary amine from an alkyl halide by an SN2. So if we use a cyanide, so remember CN- is cyanide, and it's a good nucleophile. And so if you have a cyanide ion, right, you have a lone pair here and a lone pair here, it can do an SN2 like this, and you end up with a nitrile, and then you can reduce the nitrile using lithium aluminum hydride and then aqueous workup, and that would give you a primary amine. So that's one way to make an amine. Another one is from the reduction of a primary amide. So you guys remember that you can make an acid chloride from a carboxylic acid with thionyl chloride. So after the first step, you'd end up with the acid chloride. Then you treat it with excess ammonia and you end up with the primary amide. And then we can reduce the primary amide with lithium aluminum hydride down to the primary amine. So you end up with a primary amine. So that's a second way to make an amine. And of course, in this case, we have no change to the carbon skeleton, whereas in the first one, we end up adding one carbon overall. Then we also talked about making an amine from the reduction of a nitro group. And so if you do a nitration of benzene, so this is nitration, right? You make the nitronium ion. So you make the nitronium ion, which is a very powerful electrophile. And it reacts with the aromatic ring, and you end up restoring the aromatic ring after you make the sigma complex. You make a nitro group. So this would be called nitrobenzene. Okay, you can reduce nitrobenzene by hydrogenation, or there's a whole holy host of ways that they're giving you to reduce it here. You can use iron metal, you can use zinc metal, you can use tin metal, you can use, this is tin 2 chloride. You could use tin 2 chloride followed by sodium hydroxide. And the reason you need the sodium hydroxide is because after the first step, after the reduction, since it's done in acid, you would actually end up with anilinium. So you actually end up with NH3 plus, and then you treat it with base, right? NaOH, and then you make the free base like that. So that's another way to make an amine. So let's say you wanted to make one of these amines. Well, there's a few ways to make all of them, but let's say we wanted to make this one from a nitrile, meaning a cyanide ion. So these two atoms, this carbon and this nitrogen, would come from the cyanide ion. So in that case, what would your alkyl halide be? You'd have 1, 2, 3 carbons. So 1, 2, 3. So we'll use propyl iodide. And in the first step, we treat it with sodium cyanide. And that would give us this compound. So 1, 2, 3. And then you'd have the nitrile. And then after treatment with LAH and H2O, that would give you the product. Okay. Another way you could make this compound would be from the amide. So let's say you have a 1, 2, 3, 4 like this. And then, so let's see here. Oh, alkyl halide or carboxylic acid. My mistake. So you'd start with the carboxylic acid. And in step 1, you treat it with thionyl chloride. Step 2, you would treat it with excess ammonia. That would give you the amide. So you'd have the primary amide like this. And then you could reduce that with lithium aluminum hydride, followed by treatment with H2O, and that would give you the product as well. So what we'll do on Wednesday's class, so that's going to be on the 19th, we're going to tackle these two problems here. And remember, you want to try doing it from the alkyl halide and from a carboxylic acid. So see if you can try both methods. And then after that, we'll get into preparation of amines via substitution. So we're going to talk about how amines are good nucleophiles, how we can use them to make quaternary ammonium salts, what we also refer to as quats. So sometimes we call this a quat, okay? Anyhow, so we'll talk about that. Then we'll talk about the azide synthesis. Go over the azide synthesis. We'll do the Gabriel synthesis. So Gabriel synthesis in detail. So after Gabriel synthesis, we'll talk about reductive amination. This is probably the reaction I've done the most in my life, maybe, is a reductive amination reaction. So it works really well. Very simple reaction. We'll talk about sodium cyanoborohydride, reductive amination. After reductive amination, we get into synthesis strategies, the different ways to prepare amines. We talk about acylation, which is a review. This was covered in chapter 20, so there's nothing new here. Then we'll talk about bromination of aniline and talk about how we can mitigate the number of bromines that get added by using an acyl group. So we'll deal a little bit with that. So we'll talk about that. Then we'll talk about Hoffman elimination. So if you remember Zaitsev and Hoffman, well, we're going to go into more detail about the Hoffman elimination and where it comes from. So we'll talk about Hoffman elimination. Then we're going to talk about nitrous acid. So you know what nitric acid, which is HNO3, and nitrous acid is HNO2. So we'll talk about making a nitrosonium ion, and we'll talk about how to make a nitrosamine. And then after a nitrosamine, which is kind of useless, we'll talk about diazonium salts. And then from diazonium salts, we'll get into what are called the Sandmeyer reactions. And after the Sandmeyer reactions, we do one more thing, which is look at some other diazonium ion reactions like azo coupling. And then that's the end of the chapter. All right, so pretty not straightforward. And also, much like some of the other chapters, if you go to the very end, not there, if you go to the very end of the chapter, he has a really good summary of all the reactions that are covered. So if you want to, print a copy of like the last few slides out, you can see that so far we've covered this section here. So we've covered alkyl halides, carboxylic acids, benzene. And so we're going to start with the azide synthesis on our next class. So that's kind of where we're going to start. And then we're going to finish up reductive amination, acylation, diazonium salts, Sandmeyer reactions, which are on this, the Schiemann reaction, and then diazonium other reactions, and then the formation of an azo compound, and that's the end of the chapter.